In this video, we'll show how to use the graph of a function to answer some of the questions about a process from application. So here we have a function that relates the number of units produced to the time. And it's a rational function. And just by looking at the way it's written, we can immediately sketch the graph of this function. First of all, we'll note the domain of this function. So domain is all the values except -1. And since there is no t+1 term in the numerator, we classify this as asymptotic discontinuity, meaning we have an asymptote, vertical asymptote at t equals -1. Next, we construct the sign chart for this polynomial function. So at 0 we have 0, at -1 we have an asymptote, and at -1 we have an even multiplicity. So the function is positive to the right of 0, negative, and then it remains negative again. That means if we start sketching the graph, at -1 we have an asymptote where the function goes to -infinity on both ends, and at 0 it goes through 0, so it crosses and becomes positive. Now next we look for horizontal asymptote, and since the degree of the numerator is less than the degree of the denominator, we conclude that p equals 0 is the horizontal asymptote. So that means your function approaches to p equals 0 on the right and p equals 0 on the left. And with just that much information, we know that the graph of my function will look something like this. So when it crosses the origin at 0, it has to turn around somewhere to get to that horizontal asymptote. So one thing we don't know is where exactly it turns around, and another thing we don't know is where exactly the concavity changes. And for that exact reason, we're going to find p prime and use the first derivative analysis to find the local maximum and minimum, and we're going to find the second derivative and use the second derivative analysis to find the inflection point. So let's start with the first derivative. So derivative of this function is derivative of the numerator times the denominator minus derivative of the denominator times the numerator divided by t+1 to the power 4, factoring t+1 and reducing 1 t+1 in the numerator with one of the t+1s in the denominator. We have t+1 cubed in the denominator, and we have t+1 minus 2t in the denominator. So we have -t minus +1. So it's -t minus 1 over t plus 1 cubed. Constructing the sign chart for the first derivative, what do we get? We get -1, 1. This is the signs of the derivative. All multiplicities are odd. The coefficient is negative. That means on the right side the function is negative, then it's positive, then it's negative. Then the effect that it has on the graph of the original function is that on the interval from -infinity to -1, the function is decreasing, then it's increasing, and then it's decreasing. At -1, we have an asymptote, so we cannot have minimum or maximum there, but at 1, we have local maximum. Now, to improve the accuracy of the graph, we would evaluate the function at 1. So p of 1 is equal to 1/4. So to improve that part of the graph, we are going to find 1 on the x-axis and graph 1/4. So it means the function gets up to 1/4 at 1, and that's the local max. And then it turns around and then it approaches to the horizontal asymptote at the x-axis. To determine the concavity changes, we will find the second derivative of the function. it would be derivative of the numerator times the denominator minus derivative of the denominator times the numerator. Again, I'm going to factor out t plus 1 squared in the numerator and reduce it with 2 t plus 1s from the denominator, so we'll still have left t plus 1 to the power 4. And now what's left in the numerator is t plus 1 minus 3t, so t plus 1 minus 3t plus 3, and we have negative sign in the front. So we have 4 minus 2t, which is, combining it with negative, it's 2t minus 4. And we can factor out 2 to get 2t minus 2. Constructing the sign chart for the second derivative, what do we get? Since the leading coefficient is positive, that means the function on the right is positive, but also multiplicity at -1 is even, and multiplicity at 2 is odd. That means function changes the sign at 2, but not at -1. So what effect does it have on the graph of the original function? Function is concave down on this interval, again down on this interval, and up on this interval. So at -1 we have an asymptote, so we don't classify it as an inflection point, but at 2 we have change in concavity, so we do have an inflection point. To improve the accuracy, we would evaluate the function at 2. At 2 we have 2 over 3 squared, so 2 nines. So at 2 the concavity changes, and from negative it becomes positive. So here we have inflection point. And here we have local max. So to answer the question, what happens to production in the long run, as t increases, the production goes down to 0 because we have a horizontal asymptote as t goes to infinity. So the answer is production goes down to 0 as t goes to infinity.